Okay, so last one in week 4, got one more week to go, and then I'm out of your hair. Hopefully it's been okay for you guys. Yeah, you've just started. Has everyone started the second homework? I got a question about Isabel before. No, I'm only familiar with a few. I haven't actually. I remember using one years ago. Okay, and question about homework. Yeah, just to set up it so far. Okay, doing SSH key took ages. Some started. Cool. All right, awesome. Because I don't have much time for that, so I'm worried. I'm slightly got this slight tension of covering the content quickly for you guys, but then running out of content, and I sort of have to tap dance until the end of the lecture. So we'll see what happens. So I'm conscious I probably went a bit too quickly over floating point stuff last time. So I'm happy to go a little bit over that again, unless you're finding it too easy and it's all simple stuff, but it's important. So go back over that a little bit today because I sort of went fast last time, and I don't know if that's stuff you guys are having problems with, but I'll give it a go anyway. So last one, we finished off the Git and Unix stuff. We did some basic data analysis. So, binaries. You're talking about it's playing up on me. So just making a binary file versus a text file, some basic text files that you'll see, CSVs and JSON. So yeah, part of your homework is to play around with the big JSON file from an IPython notebook. So a Jupyter notebook, so you can have a play with that and see what's going on. I talked a little bit about, big thing when you're working as a scientist is visualizations and presenting your work. So you've got to sort of get around with playing with plots. And I was trying to find, because I love all these cool pictures, and like one thing that can motivate you, if you're a mathsy type person, making cool visualizations gets, like, a lot of people love that stuff. So I was digging around for anything I'd done in the past, because I know I've done stuff before. Seeing this one, this cool spirally thing. It's like years ago, I made this one. So I thought I'd show it to you just as an example. This was in Julia. This is one of the first, another thing I did really early on in Julia. I actually found this little MP3 I made, MP4, sorry. So this is just like, instead of making a GIF, I just made frames and used a program called FFmpeg to stitch them all together, because Julia wasn't as cool as it is now. So this is solving the wave equation, just Laplace's equation on a square grid. I just made little drops fall in. So this is solving, 2D PDE. It's simple stuff, but it's fun. I enjoy doing this sort of thing. So that's easy. That's just finite differences. So we're going to do a little bit about ODEs. I don't know if anyone's done any work on numerical solution of PDEs. They tend to be a bit more of a pain to get to work. ODEs are simpler, so you get the idea. It's fun to play with visualizations. It's worth learning, and it's worth, if you're going out, like when you work in industry, like that's surprisingly large part of your job is going to be presenting results. Like if you're in that sort of role, like just a back-end software engineer, who cares? But if you're doing any sort of analysis, you're going to have to go and present things to people, and making cool visualizations can really sell. It can be misleading as well, but can be it's a really good skill to learn professionally. Learn about some image formats and how you can present results. Cool. Basic statistical summaries from a data frame. That's good. You'll play with data frames again. I tried to show you a little bit of syntax and stuff. So what we got up to was floating point numbers. So early on, we talked about integers, how you represent an integer. Now we're bringing up floating points. So floating integers, not so many problems apart from wrapping background underneath, and this thing about how do you represent the sign on an integer. Like you do this 2's complement thing, because then reuse a lot of the machinery for doing addition and multiplication. So double precision floating point is a little bit more complicated. So I had a bit more time up my sleeve this afternoon before this lecture than I did last lecture. So there was this picture I wanted to show you. So this thing about the spacing, so it's equal between powers of 2. So if you So you've got this tiny, tiny picture. Let's see if it'll let me zoom in. No, not much. But it's this banding in the floating point. So every power of 2, it's evenly spaced between those powers of 2. That's really that's the thing you want to keep in your head. So what I was saying is, like, if there's other systems of representing the real numbers on a computer. The one I think that makes more sense to me would have been logarithmically spaced. So you'd have a sign bit and take the log. If you're taking logs, you got this switcheroo that multiplication's easy, but then addition becomes harder. So floating point actually works the other way around. Blah blah blah. It's easy to add. I'm going to talk a little bit about that today. So I hope this was clear. So basically, when you've got floating point numbers, IEEE 5754, I hope I get that number right, but the electrical engineering mafia, the IEEE, they've got this standard for how you represent floating point numbers and how you do floating point arithmetic operations. So basically, you look at a floating point number, the sign bit's out the front, you have the exponent for the next few, and then the last bit is either called the significand or the mantissa. And yeah, lots of bits there. So the big thing about floating point numbers is its dynamic range. It can cover a huge range. So it actually has values for infinity, minus infinity, because it's going up in these powers of 2. This exponent to the power of 2, you can cover a lot of the numbers, and you're trying to fit all the real number line into a 32 bits or 64 bits. So this is how people have done it, and you have to learn about what's going on. I didn't say too much about the representation. There's a little funny thing here that the exponent has a sign. You've actually got this function in Julia. This is, if you want help, for an abstract float, it'll get the exponent of that. So one of these things you might look at and notice is a bit funny. Yeah, maybe this will be really hard to show though, is if I go x equals 1e to the minus 12. Let's see if this works. So the exponent thing to realize is that this isn't 2's complement for technical reasons about how you do addition and multiplication. So like we were saying earlier, in the first lecture, you probably won't remember, but there's this funny way of doing the integers where it doesn't quite match how you think you'd lay them out. It's not an offset. This one actually is by an offset. So, I hope that's clear that, instead of when you're going to negative numbers, how do you represent that? They actually shift these ones. That's a thing to know. It's a bit of just like, for you guys working at the level you're working at, it's just sort of a nice bit of thing to know. Not really important to know. It's never going to bite you, but that's the thing. But it's good to know these things. So yeah, so basically it's 2 to the power of the exponent times the significand. There's this special, I think I went through this way too quickly, but the way it's actually constructed is it's base 2. So it's 2 to the power of an exponent, and then you've got this 1 plus f. These are decaying powers of 2. So it's like, you don't do the 0, 1, that's why you get the 1 out the front, then you save a bit. Then you do times, 1 on 2, 1 on 4, 1 on 8, all the way down. All these bits. So it's just base 2 representation with the 1 taken off the front. So these guys always lie between 1 and 2. Representing decimal. That's yeah. So this thing, this really important thing is this. There's the relative. There's this minimum number. It's machine epsilon. That's 2 to the minus 52 for 64 because of how many bits you represent in the significand. Not in 32, but back in this guy, like how many, it's basically the size of this bit. It gives you the smallest jump between smallest thing you can do. That changes depending on whether you're doing float 32 or float 16. These are hanging around because of hardware. So you actually do get I think an Arduino is maybe 16-bit. And float 32-bit system architecture would be like, there's some of those still hang around. So, you know, normal desktop computer, you won't come across it so often. It's more like if you're really worried about memory and you can get away with less resolution, you might go to float 32s. So you can pack them in a bit better. You save half, you know, your memory is going to be half, or your disk space is going to be half if you can represent it with a smaller number. But otherwise, actually, in terms of architectures, they still exist and they're still around. So depending on how many bits using for the significand gives you this machine epsilon. So this part is interesting. So what this is that the relative error, I'm worried about relative errors, are always bounded by this machine epsilon. So I thought I'd go through this one. I just sort of waved my hands at this one last week. I'll do it again because I think it's interesting. So we'll go through it step by step just to make sure everyone follows it. So we've got non-square numbers. So what we're doing is we're doing you know, going to get all the integers from 0 to 100 that aren't square. So it's 4 gets taken out, you know, 9 gets taken out. It's basically all that's doing. So this list comprehension gives you all the squared numbers, or gives you all the way up to it goes way past. So it's well overkill for how big the biggest one you have to worry about is. So this guy will go out to 100 times 100. But doing the set diff between these two just leaves the ones up to 100 that are non-square. So if we take the square root of this, we're going to expect to get a real number that's not an integer. That's the point of doing that. And what we're going to look at, it's got this little tilde on top of the x. So that's the non-square numbers as float 32s. So that's a vector of float 32. And then we're going to go, if we consider float 64, have so much more precision that we can see the error in the 32-bit representation. That's what we're doing. So we're sort of going from, here's one, you look at that machine epsilon, it's 10 to the minus 16 or something off the top of my head, versus 10 to the minus 7. That's so many more orders of magnitude down that it's basically perfect. We rearrange this expression, there's this, we're going to say that the error is the difference between these two representations minus 1. So that's all these numbers bouncing around. You notice, so I was saying last time, you might want to look at Extrema. So -5 to 5.8. If we remember this eps float 32, you can pass the type into eps and it'll tell you what it is. So that guy on 2, and hopefully that is bigger in absolute value than either of those ranges. So we did, you know, up to 100, did a couple of samples of this thing, and there you go. There's this thing that's bouncing around. Bit of pretty plotting. Still got this thing around. So it's plotting the non-square numbers versus this epsilon, the error in the approximation, putting a couple of labels on. And this is going to plot on the same plot. It's going to make some bars so that we can see the limits. So these black bars. So kind of interesting. So takeaway, we're going to talk a little bit more about this. That you can sort of think of this as like it's noise that's going to be on anything you're doing with floating point numbers. There are a couple of other strange things that happen with floating point numbers that you need to be aware of doing mathematical work in programming. I'd say not so much. Oh, actually, no, I've left the last one. I still get this problem all the time, and it's like it's my nemesis. It's like all the time I get this problem, and it always comes up. So I've put an example of it happening there. It's interesting. So for me, looking at this, it's not random, it's structured. So you hear some crazy people going like crazy theories about, you know, the world's a simulation, you know, maybe quantum fluctuations are floating point errors in this giant simulation. It's like, it's not true, obviously, because floating point errors are correlated. So if it's just to show you that to you guys, like you can, using StatSpace, so we were talking about that last time, I can do the cross correlation between these errors and itself. And if I plot that, this, you know, this should agree with what you were saying, is that this, if it were a white noise process, like if it's just purely random noise, what you expect from an autocorrelation is to be a delta function. So that's the function that's 0, and at 0 lag, it just jumps up to 1. So there is an actual correlation link in this. That's like evidence that this isn't purely random. So that's another thing to take into consideration, that these errors aren't just noise. You know, close by things will give close by errors. They actually have a correlation link. They're not, you can't consider them as like white noise perturbing your stuff, like if you're trying to deal with them. Just, you know, that's more interesting. Like you can see a bit of structure in this. They're not pure, it's not just like fuzz filling the space. So that's, I guess it's a bad random noise generator, random number generator. You guys will talk about random number generators and how you might, like this, maybe this seed, what you're thinking about with this stuff is like, if you think ahead, you can go like, how do you actually algorithmically make something random? Like, what does it even mean that something is random? Like, what would an algorithm look like that took, like when you know, as we're doing these notes, we're always going, oh, using, you probably got a hint. I don't know how much stuff you've done. And you know, we're doing this thing about seeding some random number generator. You've seen this machine twister come up. If you're curious, you would have gone off and looked on Wikipedia about that. But it's actually a really interesting thing. And I'm just trying to pique your interest with this stuff, is like sideways stuff. Is we talked about, you know, another thing you can think of is like we talked about with Git. I'll just go to a repo and got these. I was saying about a cryptographic hash over here. You know, I take the data and it pumps it. That's taking an in. It's a function that takes an input and produces a random string. This is like a really useful thing in computing for doing like dictionary lookups, but also doing things like cryptography. And it's like, can you have a deterministic function that gives you a random output? Is that actually a thing that exists? And like, you know, you guys are young and smart, you can think about that stuff and whether this is actually something true. Random rounding of floating points isn't random. You know, how do you actually deterministically make something random? It's like there was this saying from von Neumann that like anyone who believes that there's such a thing is living in a state of sin. But there are all these algorithms to do it. It's like, it's not, you know, it's not the level of proof that these things are actually making random outputs. But what happens? I had a question ages ago and I didn't answer it about the order of dictionary lookups and the set membership stuff. And I sort of ummed and ahed about whether it was order 1. I had to go off and read. And the thing I was wondering about is this, it's based on this thing called a hash function where it takes an input, makes a random output out. And the thing that slows it down are hash collisions where you accidentally get two things that end up the same. That's why it doesn't quite scale order 1. As you get bigger, that's more likely to happen. So there's these things. It's like a fast function that deterministically makes random noise. It's got nothing to do with anything in your lectures, but it will come up again because you can talk about random number generators. It's super interesting. Yeah, anyway, randomness coming out of floating point numbers. So I was going to do a little bit of a diversion. Sorry, special numbers for nan, inf, and negative inf. It's going to do a little bit of a diversion and talk about, we haven't talked about it here, but I'm going to quickly give you a sketch of what addition and multiplication in floating point looks like, so you can get your head around where these problems come from. Hopefully this comes up. I've done it in decimal because I find it easier. I think everyone would agree that they're going to find it easier to look at without the head hurting about, like, you know, if I had the binary representation here, some of you might just go, oh yeah, that's cool, I can understand. Just do it as decimal so you've got an idea. This is rough. It's not actually true, but it's close enough to true that you get an impression of what might go wrong. So I'm going to say we've got two floating point numbers in decimal rather than binary, and how we might add them on a computer. So it's 1.234 times 10 to the 5, 2.345 by 10 to the 3. So the step 1 is you look at the difference in the exponent, which is 2 in this case, and then you get the smaller number and you shift it across by 2. So the powers of 10, so that they're both on the same footing. The reason you pick on the small one is that you're losing the least significant bits. So they're the small things, they matter least. So when we're going to make it as accurate as possible, we'll keep the big bits, leave the small bits. You can imagine what would go wrong if you went. Okay, so then when you've got, so in binary, going back to these logical operations, like how this might be implemented on an integrated circuit or in a CPU, is this is just a bit shift. So you're just going to go divide by 2, as many across as you go. So that difference in exponent just gives you the bit shift you need to go on the small number. So then you take the significand or the mantissa and you can add those guys together. So we've got 1.234 plus 0.234. You can just add these two, pretend these guys are integers and add them together. More complicated when you don't worry about signs and stuff. But again, this is just one of these, like the ripple ladder I talked about at the start. So you just go do that, cut off, you know, put the dot back in, 10 to the 5. That should be the answer. I didn't. I wonder if I can still do arithmetic in my head and whether I got that correct. But that's the idea of how you might do floating point addition. So you can see straight away that if these powers are really different and this isn't big enough, you know, what's going to happen? I'll actually ask that as a question. I won't leave it open-ended. It's not rhetorical. Can anyone see what's going to happen? Like if this is like 10 to the minus 3, what's going to happen instead of 10 to the 3? You have to shift 8 across and everything here is going to disappear, which is kind of annoying. It's one of these annoying floating point things. Multiplying floating points kind of the same. So in this case, if you're going to multiply two numbers together, it's easy because it's this. What you do is you just multiply the mantissa bits. So just treat them as ints and multiply them together, and then add the exponents, and then put it all back together, put the dot back in, and round it. Pretty straightforward. So you got all these steps where things can. So problems where things can happen is you can have overflow and underflow, same as with integer. Sorry, overflow where it's going over the top when you're adding too much or multiplying too much. Yeah, so these are the sorts of things, they manifest in these kooky ways when you actually have it implemented. So they're floating point. So this thing I was saying about this this image, you know, there's this spacing and some numbers that you think would be fine are not fine. That they don't actually exactly have a representation in floating point. They're approximate. So famous one would be 0.1, 1 on 10, because it's base 2. It's actually not. The closest one is something that's off 0.1 a little bit. So again, if you don't know what I'm using, big is compute the type that represents the numerical integration with arbitrary precision. So that's arbitrary precision floating point number of 0.1 is this big thing. Because this is a float 64. So this 0.1 is not 0.1. And this kind of leads to kooky things. And one of these things, so they're just masquerading as real numbers. Floating point numbers are something else. And this one will hurt your brain, is that they're not associative anymore. A little bit bigger. They're not associative anymore. So I go brackets, so associative, you know, which order do I do the operations? It's like addition is associative. In the real numbers, in floating point numbers, not so much. If I add 0.1 to 0.2 first, and then add 0.3, I get a different thing than if I do 0.2 plus 0.3, then add 0.1. So that's annoying. They're not. It's a small error. So useful function for when you're doing stuff like if you're writing, you got this little squiggly approx. So again, just tab. You can ask what that guy is. This is a really useful function to know when you're writing tests, because you don't expect when you're doing these floating point stuff, like if you're going like, I'm writing some complicated bit of maths and I have a test case where I know what the answer should be, and I'm just validating whether the function I wrote does what it should do on this case. It's a useful thing to have in your test that it approximately equals this thing because of some of this stuff starting to happen. So the default, you should be able to see, there's this rtol for a real, absolute tolerance for a real equals 0, relative tolerance equals the square root of x. So if this thing's closer than square root x, it's not going to complain. That's what this thing does. So if I, instead of going like, is this thing going to be equal this thing? If it's close enough, that's true. If we want to actually see the size of it, we can just rearrange it. And we see it's this tiny, tiny 10 to the minus 16 thing. So for reference, F's, down below, it's, in this fluff, the difference between these two, bounded by machine precision. So that's annoying. It's not a big error, but it's an error. And another thing that can happen, which is I was trying to do when I was talking about how do you add floating point numbers, if you take a big number and a small number and you add them together, it's just equal to the big number. That's terrible. So if the exponent is too different, so this is 10 to the 18 different, the little one will eat the big one. If you make these smaller, I don't know where it switched over. So 10 to the 8 is fine. You can deal with 16 difference in exponent, but you can't deal with 10 to the 9. Yeah, it's not a big error. Oh, sorry. It's just that that's the sort of thing that happens. So if you're dealing with things that are very, very different in scale, like as I was showing you through how addition might work, just waving your hands, it's a little bit more complicated for reals, but the little one will get eaten by the big one. So you got to think about, so it's a point I was trying to make early on in this lecture series, is that the abstractions of computers leak up to the top. They're all imperfect abstractions, unlike mathematics. So something about the implementation is coming up to bite you. So there might be two equivalent ways of stating a problem. And one of them will cause these sorts of problems to come through. And the other one will dodge them. And, adding a very small number to a very big number is one of these cases. Maybe, maybe if you're worried about this associativity, if you rearrange the way you're adding things, maybe you can make this one a bit bigger before you add it to that one if it's a composition of operations. So again, I wrote a little function here. Again, A is a famous one because it's not quite A. If you're going to do, I actually thought of this one because one of the questions that came up early on was like how you might do integer addition for very, very big numbers, or integer multiplication. And someone's, sorry, integer multiplication for very, very big numbers. And if one of them's small and one of them's big, you could just add it a couple of times. This is like the equivalent thing in floating point is actually a really bad idea. Repeated additions, when you could do a multiplication, will just make the error worse and worse and worse and worse. So this actually becomes, so what I've done is I've gone this is pretty straightforward. Like it's pretty, if you understand that A is not quite A, this is dead simple. And if I'm an idiot, instead of going x times, so A times n, I'm going to go A plus A plus A plus A plus A plus A plus A lot of times for n, for this thing that's not quite right. These errors get big in the end. So that's 1 by 10 to the minus 6. So do it a million times, it gets to 1 in a million. Do it a billion times, it'll get bigger still. Something to be aware of. So when you're, again, this is a trivial example. Real examples, you'll have this stuff come up. That, think about how you arrange equations for dealing with accuracy. Last one, this is the one I was hinting at the start. This is my white whale. So what I've done is I'm making a matrix. So using linear algebra because I want to do an eigenvalue decomposition. So I don't know how much linear algebra you guys have done. If I say semi-positive definite, do you get a shudder or confused or happy? Do you understand what I mean if I say semi-positive definite? Got one clear. And so much stats you've done, I think. I got lots. Good, you're all mathematicians. So straight away, if I go x dot times x, that is should be a semi-positive definite matrix. Like it's rank reduced. So there's this thing where, you know, linear independent rows. So it's not, so the eigenvalues you'd expect is like there's a multiplicity of zeros and some stuff going on. So this is a weird example. So imagine you're doing like the covariance between some measurements and there's some, you know, linear dependencies between things. You get repeated entries or something. So this guy should be semi-positive definite. If I actually go to do an eigenvalue decomposition of this, what you'll see is that the eigenvalues, there's one positive one, a couple of small ones, 1, 0, 1, and then two of these guys where they've actually gone negative. And again, compounded additions is like, you know, f's for floating point is 10 to the minus 16. That's only if you're doing one operation. Doing an eigenvalue decomposition, you can imagine the algorithm is a lot more stuff going on. You get these repeated things, and these can end up getting quite big. So this is the thing. It's like, so I guess the application I was thinking of is I used to work with LiDAR, probably said there's point clouds, and something you might want to do is to do, you go to a light, if you're trying, what we were trying to do is classify what sort of thing we were looking at with LiDAR. So a simple feature you might do is you go to a point and you get a ball around it and you go, look at all the other points around me, and this is my local environment. And you can imagine if you're scanning outside like we were, you'll get a roof, or you'll get a road, or you'll get a tree. You'll get like we were looking for all power lines, so you'd get a line. So one way you can do this is one way you can classify local geometries. You can go do this test of going, go to a point, get all the things around it in a ball, and do PCA, so principal component analysis, which is basically this. You take the covariance matrix and you look at size, relative size of the eigenvalues. Like, is this thing locally linear, which is like one big principal component and lots of little ones? Is it planar, where there's two big ones and one little one? Or is it like volume-like, so all three are big? And, you know, depending on what you're doing downstream with this thing, whether these things, you know, if you have an assumption that these guys are always going to be positive, it's going to make things explode. So, and, you know, you guys should be familiar enough, I hope, that with doing statistics, it's like every time you have a normal distribution, you're assuming normality, you're making a covariance matrix. Covariance matrix, it's, you know, symmetric, you know, there's things like, so again, talking about types and, you know, data types, having this as a full matrix is probably bad. You know this thing's going to be symmetric. So maybe you don't want to bother about keeping even the bottom half. You just want to keep the top half, and do stuff so that it always is semi-positive definite if you know this thing's going to be semi-positive definite. I've had so many bugs with this thing in my life. So more recently with this job, it's using Gaussian processes as a machine learning model, has covariance matrices. So you've got to assume they're always semi-positive definite. You'll try and do some matrix decomposition and it will go kaboom if it's not. And fighting these things is a problem. So things like, so tricks you might do is you might just take the eigen decomposition, round it, reconstruct it again so that it is fine. You might keep a certain type of decomposition so that it always stays the right way. It's a nightmare. This is the sort of stuff that will happen when you're doing numerical stuff. If you're trying to be precise, and floating point stuff will get you. It's these sorts of things. Cool. Any questions before I move on? I just did a fraction. So like, if you're assuming semi-positive definite, all the eigenvalues should be strictly, or should be greater than or equal to 0. or how many are less than 0, it's 20%, 28% of them are bad if on that metric. No questions? Cool. Okay. So starting to get towards stuff, the real stuff. So this will happen almost straight away as soon as you go to do calculus. So hopefully you can look at this, and I don't have to say too much, but this is basically, when you're doing limits, you're going to go, this is the limiting, so it's interesting with maths that these technical definitions, like the Riemann sum, we were talking about integration early on, so I've just waved my hands about it. I'll talk a little bit more about that in a little bit later. Riemann sum leads you naturally to an algorithm. So the limiting process, shrinking down these little boxes until you get to something good, that leads to an algorithm for approximating it. So a natural one to try is this definition for derivative of the univariate function. You're going to go, okay, I'll do a finite difference approximation. I'm going to go, instead of limit of h going to 0, I'm just going to fix h and say, oh, derivative's almost that, that's fine. So hopefully you can see that that's, mathematically, you would expect the limit as this h goes to 0, this will approach the true derivative. You can imagine, if you've got a function that's wiggling all over the place, taking a big step and saying, oh yeah, that's what the derivative's like at this point. That's a terrible, terrible idea. So you would expect, mathematically, errors go small. When you're starting to worry about floating point and this sort of stuff I was talking about up here, of like, if I add a big number to a little number, or consequently, if I subtract two things that are really close together, they can just get absorbed. So as h goes to 0, these two numbers become almost the same. And so you're going to start to get problems that if you're getting down to machine epsilon, this guy is so close to this guy that this becomes inaccurate because of floating point stuff. It starts to become a noise machine with correlations. So two numbers getting really close together divided by a little number will cause you floating point problems. So we've got an example here. This is really similar to your homework. I think someone said that on the chatty thing of like, is it just repeating? So it depends on how sophisticated your finite difference approximation is. So this is a forward difference. F x. So this is a function that takes f and x. H defaults to this. Yeah. A little bit, so it's a inline function. So f of x plus h minus f of x divided by h, where h defaults to the square root of epsilon. So this is this, that's like you saw that guy here, that, this useful floating point thing of like, if it's less than square root, it's probably fine. Nothing too horrible's gone wrong. Yeah, rather than having 3 argument function, you give it a default for h. So what we're going to do is we're going to look at sinusoid, or sinusoid squared. So it's probably worth looking at what that looks like. So x equals naught 1 to 10. Anyone guess what it's going to look like? I don't know if I'm imaginative enough to do it. Well, x f dot x. I'm going to broadcast this guy. So it looks like, oh yeah, so it's this shrinking frequency thing. So it's like don't actually have enough resolution to see it nicely there in my deltas. So it's this shrinking frequency as it goes up. So it's like a bit of noise. So it's like a chirp. Yeah, that's what we're going to look at. So what we're doing is we're going to look at. So we know, we know, I hate having to do calculus. As soon as I have to actually analytically do calculus, I get a flashback to 20 years ago and imagine how much I've forgotten. So you should be able, you can show, and this is easy, it's just the chain rule. The derivative looks like this. if you want to plot it, it's always worth, if you can, why wouldn't you get intuition about what these things look like? That's cool. So it's this thing that's, as it's getting faster, it's because it's got this quadratic term on the input to the cos. It's going to go bigger and bigger and bigger, faster. Cool. So that's, that's an interesting function. So we got some, let's see what we got. We've got x0, x1 equals 0.5 and 5. So different points. So the derivative is going to be slower at 0.5 from that thing we looked at and faster over here. So expect the magnitude to be bigger as it's going up. We're going to look at h from 10 to the minus 14 to minus 2. So we're stepping through this stuff, I think. This is cool. Okay. So going from quite a small number, not quite as small as you can on floating point. So it's still not down near machine epsilon. That's still still an order of magnitude of below that. We're going to look at the error by looking at the analytic expression for what the derivative should be. So we're going to look at this relative error, or so absolute relative error. So we're going to go absolute value of the relative error. So, if you just did this inside bit, you're going to get a sign thing. So we're going to take the absolute value of it. So doing this as a list comprehension at these two different points. Why are we doing it at two different points? That's what we're going to try and show. So that's the thing, we can reproduce this plot. So the interesting thing to see is that this is for the same function at different points, where this the absolute value of the relative error is minimized is different between these two bits. So it's not like you can go, there's some golden rule about the tension between floating point errors and where they're going to cause a problem, and your function, your finite difference approximation to the derivative of the function, that would change for the same function at different points, both those two things. So where this thing's minimized is quite different. And this is a log scale down the bottom. So where, if you ignore the, if you squint your eyes and blur it all out, do some sort of regularity thing where you're going to try and smooth everything out, where this minimizes, I'd be guessing like here, and this one's here, they're quite far apart in where the minimum occurs for two different functions. So finite differences are a bit of a pain. Floating point is, so you've got two things. So as you come in, your approximation dies mathematically, floating point stuff down here. And this stuff's rough as hell as well. So the mathematical one, smooth function, smoothly going to go away from the true derivative for small changes. That's maths is nice. You're going over here into digital land where the problems are annoying and rough. So yeah, so if you're doing a finite difference approximation, it's got problems all over the place. Is that clear? Hope that's fine. No questions so far? Everyone's quiet. So this is something I wanted to put in because I think I wished I'd known this at many points earlier in my career, that it was even a thing. Has anyone heard of automatic differentiation? Is that a new term? This is not symbolic differentiation, so it's not like using Mathematica to work out a... Oh, cool. Good. You're going to learn something then. Automatic differentiation is not symbolic. It's not symbolic. So it's not like using Mathematica to come up with an analytic. It's not like getting the computer to come up with this expression. What it is it's kind of magical. Seems kind of magical. So one of these things, this thing up here we just highlighted, is that finite differences have numerical accuracy issues. straight away. Like this is obvious, like even without floating point being a problem. Imagine like one of these ones, like if you're doing derivatives, and it's like for your ODE problem. ODEs are used for autodifs used for ODEs as far as I know. But you might have pragmatic reasons for not wanting H to be small anyway, because it might result in lots and lots of iterations depending on what you're doing. Suffers from numerical accuracy issues, so that's bad. Another one that's really common is, this will happen all the time, is that you want to do finite, if you have a function where this is a scalar and x is a vector, so a Jacobian. If you want to do work out the Jacobian for a function, it's actually bad. I say you've got this first reason that it's mathematically bad, like doing a finite difference is mathematically wrong, like unless H is really small, unless your steps are really, really small. There is a computational complexity issue that might not be obvious, is that this is order n function evaluations. So if you have this function and you're going to go, this might not seem like a problem if you're doing, multivariate stuff in 2-3 dimensions, whatever. But if you have a problem where this x vector is like 1,000,000, which isn't actually uncommon in practice, like if you're solving an optimization problem for something real, it is quite conceivable to have 1,000,000 control variates that you're going to actually fiddle with. And another example would be, that's more modern, I guess, people are talking about it, is you have a neural network. You can think of the error. I don't know if anyone's done anything with neural networks. You can think of a neural network as this magic black box with millions of parameters, and train it by examples. And so you have all these parameters that you're trying to minimize the error of some function with respect to these parameters. So it's actually one of these problems where you're going to go, this is the downwards direction in those parameters to make the neural network match the inputs and output pairs that I've given it in training. So you can easily have one of these big neural networks, like if you see GTP3 or something that people are talking about, the transformer networks, you can have millions and millions of parameters easily. So finite differences are just not an option for large ones that go this way. So it's actually a computational complexity problem. You're going to go, I'm going to step this first coordinate a bit, measure what happened. 1, 2, 3, 4, 5, 6. You can keep the first one as a base. If you're doing central differences, I think your homework problem talks about central differences rather than forward differentiation. If you're doing forward, you can keep the first bit, you just step the 1, but if you have to step in both directions, it's even worse. That's actually a big problem. So the modern one that I wished I'd known about, so one more problem is practical problem that I'll say, because these are two mathematical problems. Mathematical problem due to this numerical stuff, bit of a software problem. This one's a computational complexity problem of implementing this thing on a computer. There's also a human factors problem. I don't know how good you guys are at maths, but what's the chance, if you're actually writing code where it requires a function evaluation and the Jacobian of that function, what's the chance you're going to get this wrong? So you have to write it twice. It's like 2 bits of code to write, and a thing that's like non-trivial to work out depending on the function. Working out the derivative of this function with respect to the parameters can be really hard. So one of these ones I was saying is, like, I worked on a attitude estimation problem. So it's like a statistical estimate of the attitude of a vehicle. And you need to know, it's like, if you think about it as propagating errors through the system, it's like, I want a linearization of this model so I can propagate a Gaussian through and work out what the error is on the other side, given some initial error estimate. So that step of working out what these derivatives were and checking that they're right. So I'm writing lots of unit tests where I'd go, okay, I'm going to do a finite difference approximation to check my analytic derivation is correct, just to make sure I didn't get anything wrong. It took ages and ages. So there's this practical problem that if this is a non-trivial function, this derivative expression can be really, really, really hard to work out. So left out a problem there. So the modern approach is called autodiff, where you use a special type of number called a dual number. So hyper-complex number system, first in the 19th century. So this is nothing. The special thing is, so if I can get this small enough so that you guys can see. So it's A plus BE. A and B are real numbers, so it's a pair of numbers, and you have this little epsilon term, and this satisfies epsilon squared equals 0. So there's some rules for the algebra of dual numbers. If you're excited, you can go off and read about it. The big thing is the applications. Read up if you like this abstract algebra stuff. The big one is this automatic differentiation, because if you're applying product rule, blah, 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 you can get these squared terms cancelled. You can actually, by propagating dual numbers through a function. So if you have a language that's magical enough, you can, and this function and the function definition can take a dual number type, you can actually work out to floating point error what the chain rule, applying the chain rule, you can work out to floating point error what the derivative is by one pass through this function. So it has the same computational complexity for Jacobian type 1. So if the output is a scalar and the input is a vector, it has order 1 computational complexity to doing this derivative. It's complicated. If you have like something that's going from Rn to Rm, working out the best way to propagate through this thing is actually turns into a rather hard problem. That's the thing. So just give you guys an example. Zygote is the package, if you want to have a play with it, for implementing this stuff. So it has a function gradient. So I've given gradient this anonymous function of x and y is 4x plus 4y plus 1, and I'm going to evaluate it at 0, 0. That's the syntax. I don't need to show because I'm just in. So it's order 1 unless it's the first time you run the function. So there's this Julia thing of pre-compilation. Chug, 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 chug. Doing some stuff where it's pre-compiling the Zygote library. It's not actually this gradient bit. I don't know why it's taking so long. Interesting. Anyway, do it again. It's fast. So if you want to evaluate this at any point, because it's linear. This is kind of boring. It's always going to have the same gradient. You can do this wherever. Yeah, so that's this magical thing. It's like you can do this if you want to get the gradient of some function. It's fast and to floating point error. So none of this stuff about I didn't give it enough things. Let's work out that that's an int. That's surprising. Anyway, I was very shocked that happened. Yeah, so it's one of these modern approaches to doing this. So it's got these 3 advantages. It's like numerical accuracy is normal function evaluation, floating point accuracy. It's not the same problem of doing like, this one. So you could reproduce this plot-ish by just using Zygote for this guy. That would be an interesting exercise for one of you guys if you were really keen. So that problem goes away. The computational complexity problem goes away-ish. There's a bit of an overhead here, so you don't have to do n, but as this gets big, that's good. And you have this software engineering problem of like, you just have to get one function correct. You don't have to get 2 functions correct. It's like half the bugs is a big deal practically. So a lot of modern neural network libraries are doing automatic differentiation. One of the goals of Julia, if you go and read blog posts about what the guys are, people I should say, doing who work on base Julia, is they want to try and get differentiable programming so you can get the derivative of a program rather than if you've got an if statement, you'll still get the derivative out. Somehow getting all this automatic differentiation to work with that, it's cool. I can't see it working, but it'd be awesome if it does. Maybe that's just the limit of my what I think I could do. It's pretty impressive. So lots of these things for doing this. It's worth saying, because you know, when you go on, you know, if you have this problem where you've got to work out a derivative, so no, you don't have a problem. As long as you can, your function will support dual numbers. You can do it in Julia with these libraries. Cool. Any questions on AutoDiff? Hopefully that's something new and useful to you. Not part of the, you're not going to get tested on this stuff, but it's good to know. Cool. No questions? I'll go, I've sort of mistimed it by a couple of minutes, but I'll just start talking about numerical integration. So I've got there's two parts of this that I want to talk about. So integration and differential equations. So you've got some stuff about differential equations in your homework. I know what it's like. It's hard when you remember back to how much of this stuff you guys have done. So systems of ODEs, are you guys comfortable or not so comfortable? What's your level, so I can pitch it at the right level? Done a bit. Okay. Yeah. So let me know if okay. I'm not familiar. Okay. So probably a bit of overlap with other stuff you're doing. If I'm going too far ahead, please ask me to stop and pull me back, and I'll start explaining stuff a bit better. So if I've gone, there's this thing in software that you end up being a bit of a shallow but breadth. When you're in academia, you go for depth. Like you go off and do a PhD and you'll understand one thing really, 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 really well. And usually, you know, as a consequence of that, you'll end up learning lots of stuff, you know, pretty well. But when you go out doing this sort of mathematical and software engineering stuff, you end up having to know a lot of things at superficial level. So it's sort of like we're covering a lot of ground, but it's sort of what it's like as a job. So what I'm going to do is the two parts of the same coin, you know, integration, differentiation, fundamental theorem of calculus stuff is like, they're sort of the same thing. And interestingly, the numerical methods tend to be the same, have a similarity at any rate that you might not have seen. I think that's really interesting. And also it's interesting. So in the homework, I've got you to talk about something that's probably more advanced than you'd be used to seeing in one of these typical courses, about symplectic integrators. Not so worried about you understanding the details of that, but it's an interesting thing. You can try implementing something you probably don't quite 100% understand. And I think that's a useful exercise, just to push you a little bit. So that's where we're going to go. So integration and systems of ODEs. Just going to talk about univariate and a little bit about multivariate integration. Super useful, but don't want to go on. It's all these things are lots of people for a long time doing lots of work. So there's an infinite amount of depth to go into. So we'll just try and take it easy. That's where we're going next. So that will be next week. Cool. Any questions on anything from today or any homework stuff? Now we're done. No worries. Thank you for turning up. Okay, cool. That's it. See you guys later.